Okay, so now we've come to discuss matter that produces magnetic fields, in the sense that chunks of matter can develop a certain density of dipole moments inside their bulk, thereby leading to an external field coming from that chunk of matter. So what's the idea? Well, microscopically, you could imagine that the piece of matter just has lots and lots and lots of little current loops. So if I imagine just having a little chunk of matter like this chunk of matter could have tiny currents going in little loops here and there all over the place. And each of these little things here is meant to represent locally a magnetic dipole moment. Now, similarly to what we've done in the electrostatic case, when we were discussing the volume density of dipole moments, which gave us the vector, the polarization, here we will define another vector, m, called the magnetization, which is the density per unit volume of magnetic dipole moments. So you take a little chunk here, and you sum up all the magnetic dipole moments inside that, you divide by the volume, and that's the magnetization at that place in the material, okay? So matter in general will react to the presence of magnetic fields. There's a nice little section also in Purcell-Morin, I think it's in 11.5, where they discuss the effect of magnetic field on atomic orbits. So you can look at what that gives. The general conclusion is that because you've got electrons flying around protons, if you have a certain external field, you expect a certain so-called diamagnetic response from the atom. So the electrons represent a kind of current loop around the center of the atom, and this current loop, of course, is affected by the presence of an external field. If you change the field, you'll accelerate or decelerate the electrons. So that means that the electrons start, if you want, moving faster or slower, and that changes the actual magnetic moment associated to that atom. Okay, but I'll let you read through the details of that, because it's like basic physics, which you might even have seen in quantum mechanics. For our own purposes, the only thing that we need to realize is that complex matter reacts in lots of possible different ways to the presence of an external field. The most typical reaction of a chunk of matter to an external field is the diamagnetic response. So that means that when you shine an external field, locally, the little pieces of matter will develop a magnetic moment which tends to oppose the external magnetic field. Yeah, so these are diamagnets. Now, there are many other complicated types of responses that can be classified. I think there's probably about 20 different types of responses that you can think of, but there are three general categories that are the most important. Besides diamagnets, there's also a possibility of having so-called paramagnets. So paramagnets simply have a magnetization developing in the direction of the applied magnetic field, okay? And perhaps most interestingly and most surprisingly is in terms of possible responses is the case of ferromagnets. So ferromagnets are quite cool because what they have is a spontaneous magnetization. That means that even if the external field vanishes, the chunk of matter has kind of permanent magnetic moment associated to it. So you know that because you've seen you've seen permanent magnets before. That's exactly what they are. The physics of these things is really quite interesting. It's got to do with the physics of phase transitions and whatnot. So if you carry on in physics, you might end up studying quite a lot the physics of magnetic materials as a function of external field, temperature, and all these things. It's really quite complicated and rich. But as far as we're concerned, we're going to discuss mostly about diamagnets and paramagnets, and in fact, we'll kind of chunk them up into one simple treatment when we come to discuss dielectrics. Okay, so for all of this, I would refer you to Purcell-Morin sections 11.7 and also at the very beginning, 11.1, there's a discussion of the basic physics of these objects here. So if you read through that, you'll be all good.